Section 3.2 is all about measures of dispersion. The word dispersion means spread. So measures of dispersion are meant to describe how spread out the data are. In other words, they describe how far on average each observation is from the typical data value. So what I've done in example 1, just to give you an idea of what we're looking at here, is we're going to compare the IQ scores of a random sample of 100 students from 2 universities. So we have 100 students from University A and 100 students from University B. We've calculated the mean IQ score for both universities already to be 100, so we have the same. The histograms below show the distributions of these IQ scores, and we of course grouped this data so it has a lower class limit of 55 for the first class with a class width of 15. Okay, so let's draw some conclusions from this results. For both of these, the average IQ is 100. But if you notice, University A has a bell curve that is more spread out than the bell curve of University B. So the conclusion we can draw here is that though the mean is the same, the histograms suggest the IQs at University A are more spread out or dispersed, which tells us then that University B's data might be more reliable because the students will be between, let's say, plus or minus 10 points from the mean more often than they would be if we took a random student out of this spread, because the chances of us picking somebody down here is higher than this one because there's literally nobody that far away from the mean. So spread gives us a good idea of how centralized our data is to that mean and median that we learned about last class. We're going to continue to add measures of dispersion into our toolkit. The first one we're going to learn about is called the range. The range are, now this is not like domain and range, this is statistical range, is the difference between the largest and the smallest data value, which I guess is the same kind of idea as domain and range on a graph. So we're taking the largest minus the smallest data value. Now let's think about this for a second. Is range going to be a resistant measure? Resistant means that it is not affected by extreme measures. But if we're taking the largest and the smallest data value, then those are the extreme measures. So no, it's not going to be resistant because it is affected by extreme values. So let's go back to our example for the students who took that exam in that introductory statistics class. We have the 10 students' grades here. Let's compute the range for this data. To do so, we need to know the largest or highest score and the lowest score on the test. And so we would find range by doing 94 minus 62, which is 32. So the range of this data is 32. That's the difference between the highest score and the lowest score. The next type of dispersion measurement we're going to find is called standard deviation. Standard deviation specifically for a population. Now I need to point this out. This page is all about standard deviation for a population. But standard deviation itself is about the deviation about the mean. That just feels like I've said the same words 8 times because I kind of have. The formula that we're going to use for standard deviation is always set equal to this lowercase Greek sigma. That's the symbol for population standard deviation. And the formula is here, sigma equal to the square root of the sum of the observations minus the mean squared divided by n, where n is the number of observations in the population. So let's make a quick point here that we would need to calculate the mean before we do anything with standard deviation. Luckily, we've already done that, and actually, though this looks like a complicated formula, it's really pretty easy to compute. So let's go ahead and compute the population standard deviation of those test scores from Table 8. Now, we learned this last class, and if you look back in your notes, we found the population mean for this data to be 79. So that is the same number all the way down this table. 79, 79, all the way down this table. Easy peasy. My next column in this table asks me to find the deviation about the mean. What that means is I'm going to subtract the observation minus the mean. Mathematically, for this first row, that's going to be 82 minus 79, which, yes, is 3. For the second row, it's going to be 77 minus 79, which is negative 2. Be sure to put that negative. The third row would be 90 minus 79. Do you see the pattern here? And so we go all the way down the table. Again, you can compute all of these. In fact, I hope that you would stop and actually make sure that my math is mathing, because we've all seen what I've done by myself sometimes. But we get the deviation about the mean, which is the observed score minus the population mean. But then we need to square those deviations about the mean. So we're going to take 3 and we're going to square it. We're going to get 9. We're going to take -2 and we're going to square it. We're going to get 4. Notice that I'm squaring the entire -2 and not just -2 squared in my calculator. Put it in parentheses, or better yet, just do it in your head. 11 squared is 121, -8 squared is 64, -17 squared is 289. Then you have 121, 25, 25, 225, and 81. So we have the squares of the deviation about the mean. Again, pause the video real fast and double check my math because we get it. To continue building my eventual formula, which is going to be here, I'm going to sum the squared deviations about the mean, which means I just need to add up all of these numbers. 9 plus 4 plus 121 plus 64, 289, 121, 25, 25, 225, and 81 adds up to 964 square points if we're following our units. The next thing I'm going to do to, again, get the inside of this square root, the radicand here, going is I'm going to divide by the number of observations. And the number of observations is 10. That means this becomes 96.4 points squared. And then last but not least, because since this is what I'm looking for, sigma, my population standard deviation, is the square root of that number. So I press square root on my calculator and then type in 96.4 or go highlight that answer. And we get that the standard deviation for this data is 9.8 points. Now, calculating these by hand, especially when there's more than 10 data points, can be really annoying. And this is where Excel is going to come in handy. It's impossible for me to show Excel on my, what's this called, iPad. So there's going to be a second video that I need you to pause this video and flip to so you can watch me do this example in Excel, because I'm going to need you to be able to do these examples in Excel. We can do this in your calculator. It's not hard, but when the data sets have like 50 data points, you're not going to want to type that in your calculator. You're going to want to type that in Excel. It's way easier to fix typos there and a whole bunch of other things that we'll get to later. These are all of the formulas that I'm going to use in the video over there. Anyways, pause this video, flip over to that video. Yep. I hope you pause the video. Okay, moving on. So that was, on the other page, was standard deviation for a population. There is a completely different formula for standard deviation of a sample. In fact, we use an entirely different letter. We're just going to use a lowercase s. The sample standard deviation, s, of a variable is the square root of the sum of the squared deviations about the sample mean. That sounds familiar. That's what we did before. This time divided by n minus 1. I want you to highlight that in a color we haven't used yet today. N minus 1, where n is the sample size. So again, we have this formula that we're going to be using. It is the square root of the sum of the difference of the square root of the sum of the squared deviations about the sample mean divided by n minus 1. So we will need the sample mean just like we needed the population mean, sorry. Now this n minus 1 is called the degrees of freedom. We need degrees of freedom in a sample compared to a population because we are less sure if our sample truly represents the population standard deviation. Same way in the last notes, we found the population mean and the sample mean to be close but different. We have to divide by one less number to allow for this kind of wiggle room between a sample and a population. But the formula works really the same. We're going to compute the sample standard deviation of the sample containing Jennifer, Juan, Ryan, and Dave's test scores. So if we are doing this with the table, that sample is going to include Jennifer's score, Juan's score, Ryan's score, and Dave's score. Okay, we need to calculate the X bar for this data. So if I come over here to the side and I calculate x bar will be 62 plus 88 plus 77 plus 68, all divided by 4. That's my sample mean. And I'm going to get 73.25. Just kidding, 73.75. So that is the x bar for each and every single row. That doesn't change because that is our sample mean. You've seen this kind of setup before where now we're going to take the observed data value and subtract x bar. I'm not going to show my work here. So 62 minus 73.75 is negative 11.75. 88 minus that sample mean is 14.25. 77 minus the sample mean is 3.25. And 68 minus the sample mean is negative 5.75. We're going to square those terms. And you're going to keep as many decimals as possible. So in this case, we're going to keep 4 decimals. 138.0625, 203.0625, 10.5625, and 33.0625. Again, I'm just squaring these terms here. Building up to our sample standard deviation equation, we're going to sum those values. So I'm going to add up these guys. If I add them all up, I end up with 384.75 square points. If I divide those by the degrees of freedom, remember our sample size was 4, so I'm going to divide by 3 and minus 1. So dividing by 3, we have 128.25 square points. And lastly, finally taking that square root of the number, so we get the sample standard deviation, we square root that number, we end up with 11.3 square, or points. Not square points, just points. Now again, I'm going to have you pause the video and look and see how to compute this using Excel or Google Sheets. There is also going to be a moment where I show how to do this on the TI-84, just in case you have that tool at your disposal. But for the most part in your life, oh, here's a typo. This should say S, compute S, because we are no longer doing population standard deviation, we're doing a sample. You get it. Please go ahead and pause the video so that you can watch the electronic version of how to use technology to do this. I hope you pause the video. So is standard deviation resistant? Great question. So let's think about this. Suppose Jennifer's score was a 26 instead of a 62, like she did real bad. The population standard deviation increases from 9.8 to 18.3, so our data spreads out. Clearly, that means the standard deviation is not resistant. That's going to be huge for us here, that standard deviation is yet another measure that is not resistant to those extreme values. Therefore, standard deviation should really only be used for distributions that do not have extreme observations, that really do follow that symmetrical bell curve. Now, what have we found when we found standard deviation? It's a great question. So standard deviation, remember, represents the typical deviation from the mean. As such, the standard deviation may be used to judge whether a particular observation is far away from the mean data set. So for example, let's say that this is our information. Is a measure of 31 centimeters far from 25 centimeters? And it depends on how you're measuring this. So let's say here's our mean data, 25, and here's 31. They're not that far if our standard deviation is 6 centimeters, because it's only one standard deviation away, 6 centimeters. However, if this is 25 and then look over here, this is 31, but our standard deviation is only 2, that means it took 1, 2, 3 standard deviations for us to get from 25 to 31. And so then the answer is yes. A good rule of thumb to consider is that an observation is far away if it is more than 2 standard deviations from the other observations, such as the mean. And when comparing two populations, the larger the standard deviation, the greater the dispersion or spread of the distribution. So let's review back again with our university example from the beginning of the notes. I have computed the standard deviation for you using, it's called StatCrunch. You don't have to know how to use it because I'm going to teach you other ways. But we found that the standard deviation for the 100 people from University A, IQs, and then B are 16.08 and 8.36, which means that the sample standard deviation from University A is larger than that of University B. It's a bigger number. Therefore, University A has IQ scores that are more dispersed, which again makes sense visually in the histogram. Its data is more dispersed, so it has a higher standard deviation. One of the other measures of dispersion we can talk about is called the variance of a variable. The variance of a variable is really just the square of the standard deviation. So population variance is sigma squared, and sample variance is s squared. And the units of measure in variance are square values. Now, notice if you look carefully at the formulas for standard deviation, you'll notice that this value underneath the radical that we found in our tables represents the variance. So if we do this in the method I taught you, we are also finding variance when we find standard deviation, so during that process. So if we think back to example 3, which is where we found a population standard deviation for the test scores, we had the standard deviation to be equal to 9.8. So if we square that value, then population variance is just that number squared. So if we do 9.8 squared, that was going back a step, 96.4 square points, which was the value in our table the step before we found standard deviation. And again, if our sample standard deviation is 11.3, we square that term or go back a step in the problem, 128.25 square points is the sample variance. So again, you can find variance while finding standard deviation. Just go back a step or square your final answer. Now, all of this turns into what's called the empirical rule. We have a lot of conclusions we can draw from our bell curves or our bell-shaped data. Here's what we know. If a distribution is roughly bell-shaped, then we have the following conclusions. Now, before I read the conclusions, let's see what we're looking at here. This is the population mean, or the sample mean. Okay? If we look, we have moved one standard deviation above or below it at that first kind of spread we have there. We have moved 2 standard deviations away at the second arrow. And this tiny little space here is 3 standard deviations away from that population mean, which is how we found each of these values here. So 1, 2, or 3 standard deviations above or below. Now, what do these different pieces mean? Okay, if you are within 1 standard deviation of the mean, that is 68% of data will be within 1 standard deviation above or below the mean. Okay, 34 above, 34 behind. If you jump 2 standard deviations, 95% of your data is going to be between these 2 points. So that's 34 plus 13.5 on this side and the same on that side. And if you jump 3 standard deviations away from your mean, then 99.7% of your data are going to be within 3 standard deviations, which means we can make a lot of really good conclusions about our data if we know that it's roughly bell-shaped and we know the mean and the standard deviation. So let's see what this looks like in practice. Example 8 is using the empirical rule to make some conclusions. We're going to use the data from University A in Table 7 at the very beginning of class. So all 100 of those have been summarized below, and we're going to put them into this bell curve. We know that we found the sample mean to be, sample mean to be 100. And in the couple examples, maybe a page back, we found that the sample standard deviation was 16.08, but we're going to call that 16.1. So before we start to look at these conclusions, let's go ahead and fill out the numbers of this bell curve. We know that the mean is going to be 100. Boom, that's the center of it. the next tick mark away above and below should be 1 standard deviation above 100 and 1 standard deviation below 100. So that's going to be 100 plus 16.1, which is 116.1, and 1 standard deviation below it. So 100 minus 16.1 is 83.9. If we keep adding standard deviations, so take this number and add 16.1 again, we get 132.2. Add a third standard deviation, we get 148.3. Going the other way, 2 standard deviations below the mean would be 67.8, and 3 standard deviations below the mean, so subtract 16.1 again, we get 51.7. Okay, these are the IQ values that are 1, 2, and 3 standard deviations away from the mean. Let's determine the percentage of students who have IQ scores within 3 standard deviations of the mean. If you are 3 standard deviations above or below the sample mean, then that means you are at 99.7 degrees of the data points will be there. So 99.7 of the students in University A will have IQ scores between 51.7 and 148.3. Let's determine the percentage of students who have IQ scores between 67.8 and 132.2. Well, I recognize those as these numbers, 67.8 and 132.2. That is the sample population minus 2 standard deviations, and the sample population plus 2 standard deviations, which means since we are 2 standard deviations away, we are 95% of the data. So 95% of the students at University A will have IQ scores between these two values. Now, based on the actual table at the beginning of the section, the actual percentage of students who have IQ scores between 67.8 and 132.2 is 96%. Does this actually fit with the empirical rule? At 100%, yes, it does. 95% is very close to 96%. So this makes sense. Now, according to the empirical rule, what percentage of students will have IQ scores above 132.2, which means we're looking at the number of IQ scores in this little bit and this little bit. Now, we have those percentages here on the theorem section. So if we write down those numbers, that this is 2.35% and this is 0.15%, all we have to do is add those two numbers together to get the percentage that would be above 132.2. So 2.35% from the space between 2 standard deviations and 3 standard deviations, and 0.15 for the little space above 3 standard deviations would give us a total of 2.5% of students who will probably have an IQ score above 132.2 at University A. Now again, before I close this video, please make sure you did actually stop and go back to see how to do these kinds of problems on Excel and the calculator, since it's a separate video. If you have questions, I'll be back next class to answer.